Okay, well, since I had the chance to run back upstairs a second time, I went ahead and moved that file over. So here is your project instructions. So this is posted out on D2L. It's in the homework module, but so this part I was just talking about. Select a data set and write a proposal for your project. You don't have to write a proposal, but email me and say, here's where I'm going to get my data, here's the variables I'm going to use, that kind of thing. Just something brief, but then start going. It says, applying the methods learned in this course, perform an analysis of your chosen, it says series, that's left over from time series, your chosen data set, right? Demonstrate appropriate use of technology, SAS software, or Excel. Follow your plan, blah, blah, blah. All right? Let me zoom this up just a little bit. I want the report to be fairly brief. It doesn't need to be long, but I want it to be the way you would write up a report for a science class, or for if you're going to write a paper and publish it in a journal or something. All scientific articles have that same basic setup. An introduction paragraph or whatever that says, I got data from here, here's the problem I want to solve. Maybe it's, people in this country have health insurance, a little bit of background about what it is and why you're interested in the problem. Okay? Then a description of the data set. What variables does it have? How did they collect the data? What year is it from? All this kind of stuff. Just it doesn't have to be long, but a description of the data set. And then statistical analysis. A section. I call that statistical analysis in a more general scientific type paper. It would be called methods. The methods section. What did I do to answer this question? So for this class, statistical analysis, describe the modeling strategy, the steps you went through, the results of the model building process. How did you decide to use the model you used? And then give some predictions and examples. One of the things I always, when I advise people on like student paper competitions for KME or things like that, I always say, take your model, and yeah, the mathematics is interesting, but what's even more interesting to people are some examples. Like, if you look at the 14th observation in the data set, that one doesn't fit the trend of the rest, and talk about it a little bit. Here's an example. Here's what the model would predict for that guy or that whatever, that type of family, and it's not getting it right for these reasons, or it is. Get one that where the model's working perfectly for this one, right? And tell why you think that is. So give some examples, just something interesting from your data. So it's not just all boring stats stuff. And yeah, it can be boring. And then conclusions and discussion. And again, that can be pretty short, but in the discussion section, I always advise people to talk a little bit about limitations. Like, what I did was wonderful, but you have to take into consideration that this doesn't include people from the Northeast, or whatever, any kind of limitations that are in there, right? The data didn't come from a random sample, or whatever it is, right? And sometimes it's limitations of, if I'd have known more statistics, I could have done more with this, but this is a first course in regression, so what would be interesting in the future is to do, anything like that. Put that in the conclusion and discussion section. All right? And then, very importantly, be prepared to discuss your project orally with the class. All right? So you're going to do an oral presentation of this during that last week of class. All right? Now, if you had me for time series, you had to do that already, so you're used to that. It's nothing too intimidating. If you're willing to get up there and talk, then you pretty much get all the points for the oral part of it. Right? I'm not going to grade you harshly on that. But I think it's important that you do both of these things while you're in school. Kristen can tell us, when you're out on the job, you're writing reports all the time, or you're explaining stuff to people all the time that don't know your subject. Right? So you have to be able to learn to communicate with them. So learn to communicate. Don't give your oral presentation as if you're talking to your stats professor who knows all the statistics in the whole world.
It's true. Talk like you're going to accountants.
Yeah, there you go. Talk like you're talking to accountants, right? Or you're talking to the VP of something else who was a business major. And we all know business majors don't have to know much of anything, right? I'm just joking. But they don't know statistics. So approach it from that perspective, which helps you because you don't have to worry about being real technical in your talk. You don't have to explain, how this beta parameter was estimated. Keep it simple. You've heard of the KISS principle, right? Keep it simple, statistician.
Hey.
Yeah. So, there you go. It's I believe I said 30 points. So it's a big project.
Are you adjusting that since we're going to have to do the proposal? Or is it
No, it was 30 points all along. It's just the proposal was 10 points and the rest was 20 points, and now it's just all 30.
So we automatically get 10?
I can guarantee you everybody will get at least 10 points. I can guarantee you that. Okay. The project is to be done in groups of 2 or 3. Right? So, do the project. Kristen, since you're not on campus, if you want to do it by yourself, or you obviously don't have to do it, but you're going to maybe do something with your own data for work. If you want to do that, great. But the rest of you should pair up or get in groups of 3. Don't go more than 3 in a group.
So we can really just test whatever question we want to answer.
Yes. Yes.
We
That's a
can find data.
dangerous way to answer that question, but it has to be some kind of a reasonable data set, right? I have to approve it before you do it. But then, yeah, you're pretty much free to do whatever you want. And we're learning logistic regression right now, and I will finish that today. And then I was looking at the calendar. I'm actually a day behind the syllabus. It says that today was going to be survival analysis, and it was the only day. And then next week, we're going to review on Monday and test on Wednesday. Right? So test a week from today. And then the following Monday, the Monday of Thanksgiving week, that is on the syllabus as a project work day. So come to class with your laptops, and you can get to SAS and work together and start writing stuff and whatever. And then that following Monday, you got to be ready to give your talk. Okay? We are about out of semester. I wish I had one more week, because boy, I could really nail you on. No, I could really give you some information on survival analysis. I've never yet managed to fit that in, and it is an important topic, but I guess not one that you have to
We
do.
barely got to logistics regression when I took it. I think
Yeah,
that
this
was
is-
the last one.
Yep. We got
That was
this.
after our project, so
Oh, really?
I think so.
So, okay. Any questions?
So when are we doing survival analysis?
We're not going to get to it.
Oh, right.
Yeah, we're just not going to get to it. I've never ever got to it before, but I thought I had my syllabus redone this year. I thought I'm going to get it in there, but it just somehow I fell a day behind, and so we're not going to get to it. I only had one day slotted for it anyway, but it's not critical that you know how to do it. But
like, what is it? Just like brief? What is it?
survival analysis. It's basically the same type. It's similar to logistic regression in the way that the model is fit, but it's the same idea that you have a regression model, but now it's to predict survival. Logistic regression predicts yes-no variable, and you can think of survival in those terms. They survive or they don't. But it's more complicated than that, because most of the time, if not all of the time, when you have survival data, you have subjects who live a certain amount of time and then die. I shouldn't say survival necessarily, it's time to event. They go a certain amount of time and then the event happens. It might be the event is they take out an insurance policy, or whatever. But just it's an analysis of time until something happens, right? So I'll say survival. So time until they die. But then you have other people who are still alive. They haven't died. But I know that they lived at least this long. And those are called censored observations. So taking into account the censoring makes it a little more complicated than logistic regression. But otherwise, it's kind of similar.
So if you have like an incomplete data set or like patchy data set, that's what.
Well, it's not even that so much as, some people, my experience is all in clinical trials with survival analysis. We do oncology trials. And some people don't enter the trial. Not everybody starts the study on day one. Some people, it might be a 5-year trial. Some people don't come in until year 4. And so then you don't get much data on them. But you got some, and you might as well use what you got. So those are censored observations. So anyway, any questions about the project? Has anybody already got their data set identified? What they're going to use? Just sort of?
Sort of. I didn't realize it was a group.
And if anyone wants me in the group, I'll be glad to be in the
Yeah, I
group.
thought it was
I
a
have
solar
programmed
project.
graphics.
What's that?
So I thought it was a solar.
I think when I first talked about it, I did say solo project, but I want to make it a group project. I want to make it a group project and I have grades with me. No, not really.
It's almost like turning in.
So really cool.
But I actually, I was talking about preparing you for your career, and you need to learn to communicate. You need a little bit of writing skills, a little bit of oral presentation skills, but also learn to work with other people. Right? And for math nerds like us, sometimes that's not that easy. Right? So you need to learn to work in a group too. So it's helpful. All right. So let's go on to logistic regression. And what I'm going to do, I had started this last time, but I didn't have this yet. I remember I told you that for copyright reasons, I can't Xerox a whole chapter out of the book and just give it to you. Well, don't tell anybody. Oh, I just got it on video. So what I did was I copied one section out of the book, and it's this book. It's our old one, which I like this book. It's geared to the actuarial field, but it's regression analysis and time series is in here too. But the book was a little hard for people to understand, and it was also just full of typographical errors. And it just got to be really annoying. You couldn't trust the answers in the back to a problem or anything like that because a lot of times there were errors. So I moved away from the book, but I still go back to it because it gives some really good examples using real data. Whereas our current book doesn't use real data hardly ever. So anyway, this whole section out of that book is using the MEPS data, which is one of your options for this project. The MEPS data has, 200 variables in it. So there's plenty to do besides what we're doing here in that data. Great. So the MEPS data, they're describing it a little bit, and what they did was take a random sample of 2,000 individuals from the full 2003 MEPS data set. Right? So to make it manageable for this textbook, they just took a random sample of 2,000 of them out there. Okay? So what we're going to do for the logistic regression talk today, the dependent variable will be an indicator of positive expenditures for inpatient admissions. What? They got hospitalized. Right? So we started that last time. Yes or no, they got hospitalized. So that's the way it's in the MEPS data. Positive expenditures. So the number in there is bigger than 0. Right? So expenditures. So that's what the MEPS stands for, Medical Expenditure Panel Survey. Okay, so the explanatory variables, let's just go down to that. Explanatory variables that help explain whether or not somebody gets hospitalized could be demographic factors, right? Age, race, location they lived, anything like that. So that's what they're talking about there. Regional impact, economic behavior, personal inherited wealth, social habits, all these things are in this data set. And this data set has a ton of stuff. We're only going to be talking about a small subset of it here. So, the demand for medical services is thought to be influenced by individuals' health status and their education. So, in the maps, they ask self-rated questions about physical health and those kind of things. You know, how healthy do you think you are? And then they make categories out of income. Remember the poor and the in poor and all that we looked at last time? The in poor turns out to stand for near poor. They're near the poverty line, basically. Okay? So I don't have to read all that to you, but just know that we've got all these variables that are going to help we're going to use to try to help predict whether somebody gets hospitalized or not. So this table is summary statistics on the different variables. And I can't show it all in one screen without making it small. But so demographic, age, and gender. 1 is female, 0 is male. Right? And percentage of data, I've got age in years between 18 and 65. So the mean is 39 years old in this data. And then we have 52% female and 47% male. Almost 53% female. And then in this column it says percentage positive expenditure. What is that saying? Yeah. So 10.7% of females got admitted to the hospital during that year. Right. So that's what that is. So for each of these subgroups, that's what that column is indicating. Right. So ethnicity is in Asian, Black, Native, White. Then region of the country, Northeast, Midwest, Southwest. Education is college, high school, and then the reference level is lower than high school. So there's 3 levels. Less than a high school education, a high school education, and then some college. Degree or at least some college. Self-rated health, poor, fair, good, very good, and then excellent. Reference level is excellent. Okay. Self-rated mental health status. So MN is mental health, and it's either poor or it's good to excellent. So it only has 2 levels. Right? And then I'll scroll down, but any activity limitations. Oh, that's what that was. Remember last time I said any limit. I couldn't remember what limit was, but it's limitations to physical activity. So a lot of times doctors will give, particularly elderly, frail patients, they'll give them daily activity tests, right? Can they button their shirt? Can they walk up and down a flight of steps? Anything like that? Well, those would be limitations. Right? So do they have any kind of functional limitation or not? Right? Well, look at that variable. 14.6% that said yes, they have physical limitations got hospitalized versus 5.9% if they don't have. That might be an important predictor of whether or not you get hospitalized. And then income is high, medium, low, near poor, and poor. Sorry for pausing, but reference level is poor/negative. Negative. How do you have negative income? Well, yeah, I don't know. If your expenses are outweighing what you got coming in, I guess they say that's negative. I don't know. Or maybe you're giving money away. I don't know. And then insurance coverage. 1 if they're covered by public-private health insurance. 0 if they have no health insurance. Look at that one. Do you think it would be an important predictor of being hospitalized? 3 times the rate. 3% of people with no health insurance got hospitalized. 9% with health insurance got hospitalized. 3 times the rate. So, possibly a very important predictor. Now, this is typical of real data. You got a lot of X variables. So it's a model building process. Yeah.
Is that 9%, 3%, is that up to 77? That's sort of the total people.
9% of the people in this group got hospitalized. So overall, that's down here, it's blurred out, you can't read it, but it says total. So it's saying ignore all of these variables. In the data, 7.9% got hospitalized. So 92% of people did not get hospitalized, 8% of them did, and we want to predict who those 8% are going to be so that we can know whether to give them insurance or not. Okay, so talked about all of this stuff, I think. Let's just go right to their modeling, and then we're going to go to SAS and do it. But let's look at their output from, they ran different models and using different methods. We'll ignore this column, probit model. Probit analysis is very similar to logistic regression analysis. It's just a different way to do it, but the results are very close. So basically we're going to look at full model and reduced model. Right? So the reduced model was, if you look at it, anytime there's a blank, then that variable was removed from the full model. Right? So they fit the full model, then they identified variables they didn't think they needed. Well, they removed age, and they removed mental health. Remember, that was a binary variable, and they took it out, and I think there's one more down, but almost there's no difference in the two buckets. So I'm just going to fit the full model, and we'll talk about that. But look at the parameter estimates, and then they reported T ratio. That's not typical, and I don't recommend reporting the results of an analysis using T ratio. Remember what I was talking about a minute ago? Present data to somebody who doesn't know anything about statistics. If you put T ratio up on a slide, somebody's going to raise their hand. What's a T ratio? And you're sitting there thinking, I know they don't know anything about statistics. How am I going to explain this? So then what's your answer?
It's the ratio of T's.
And they're going to go, well, what's a T? So your answer is going to be, oh, don't worry about that one. So then, of course, they're thinking, so why'd you put it on there? So this is not recommended. A p-value might be nice there. Almost everybody understands what a p-value is. They may not know what it means, but at least they know that it's the results of a hypothesis test. What's better is odds ratio. Put an odds ratio there. Right? We talked about odds ratios last time. We'll demonstrate that with SAS here. So now let's just look at it. It didn't come through on my Xerox copy here, but I had written in the margin of my book, mistake. Notice that we talked about this last time. What race is missing here? White. Right? So white is my reference race. No problem there, except there's another one missing. Asian, Black, Native American, Hispanic is missing, and other. Right? There's lots of other races, not a lot, I mean there aren't that many races, but there are races, other races than these three and white. Right? So other is lumped together with white, since that's missing too. So that's kind of an error that in their analysis. So I recreated their race variable, which did have another category. They have a variable called race, and it has other and white, and then all of these. But then they made dummy variables, and they forgot to put the other one in there. So it got lumped with white. And that's part of why I didn't like this book, because stuff like that happens all the time. But we're going to use it as is. I guess before I run it in SAS, the T ratio, you guys know what a T ratio is, right? It's not the way you're used to hearing it said. What is a T ratio? T-score, T-test statistic, right? And it's the ratio of the parameter estimate to its standard error, right? So just eyeballing it, how big does a T ratio have to be before you say, oh, that's statistically significant? About 2. So that first one, intercept, but that doesn't really help us, but the intercept is clearly not 0. Then the next one, age, has a t-ratio of 0.18, and that's why in the reduced model they removed it. It was not significant. Age was not a significant predictor of hospitalization. Next one is 3.8, that's important. Then small, small, small. Northeast is kind of big. These are kind of big. So region of the country seems to be important, but race does not seem to be important. College or education. So there's 3 levels of education. The reference group was less than high school, so those are not significantly different.
So does that say that younger people are not significantly less likely to get hospitalized?
That's what that's saying, yeah.
Really?
And these were all age 18 to 65 in this data. Now that cutoff at 65 makes me think, oh, okay, yeah, I can kind of see that. But if it was above 65, then age starts to get real important, right? But up until you're age 65, 65-year-olds probably aren't that much more likely to get hospitalized than 25-year-olds because nobody's getting hospitalized very much. Right? But after 65, then it starts to go up. Okay, so that's what that column is. It would be better if we had p-values there and odds ratios. So let's run this in SAS. So in SAS, I showed you this last time, but I was kind of in a hurry. But I created this new race variable, race2, to be equal to race. But if race is other, then race2 is white. So what am I doing there? What does that little bit of syntax do? It puts them together. It says if the race variable says they're other, then I'm going to lump that together with white, because that's how they ran their analysis with dummy variables. Right? So if I want to run it using the other group, then I created a dummy variable for other. So we can show the difference and see if it makes any difference. I doubt if it does, but okay. So personal health status, gender, age has already been, I didn't have to do anything with age. But let me run this to load the data. And I'm calling the data health expend, and it will be stored in the work directory. Okay. Proc contents, I don't know if you've used that or if I've shown you that before, but sometimes that's interesting to look at before you start your analysis process. It tells you not only what variables are in the data, but what's the name of that variable, right? So here's a list of all the variables that are in this particular data set. Not all of them are being used, but most of them are being used in the analysis. Okay, so if I run this, this is the full model in that table we were just looking at. Go clear to the top. Start working our way down through here. So, tells us the name of the data set, what's the response variable, 2,000 observations. We had 157 of them that were hospitalized and 1,843 that were not. If you take 157, divide by 2,000, that should be that, I forgot what it was, 7.9% or something? Yeah, it was just about 8%. And then class level information. We have region with 4 levels, education with 3 levels, personal health with 5 levels, and so on. What I ran this analysis, I forgot to point it out while I was looking at the code, so I'll go back and show you that. But I didn't run this using all those dummy variables. I ran it. Proc Logistic will allow you to do it either way. I showed that last time, right? We did gender as a numeric 0-1 variable, and then we did it with character string M's and F's, but then you have to make a class statement. And class statement, I like using a class statement because it gives me these type 3 analysis of effects. And notice the degrees of freedom. I've got income with 4 degrees of freedom. So that's the partial F test of all 4 of those 5 dummy variables altogether. Right? There were 5 levels for income. You leave one of them out as your reference group, and you got 4 dummy variables in there. Well, if you use the dummy variable way of doing it, you get a test for each of them compared to the 5th one, the reference one. If you use it as a class statement, then you get what's equivalent to a partial F test of all 4 of them together. So it's a test. So I get that here. Right? So look at these p-values. Age. What do you notice? It's not significant. Okay, that's what we saw. Gender. Highly significant. Now remember, these are just like in multiple regression. These are variables added last tests, which means gender is significant even after explaining everything we can explain with all the other variables. Right? There's still variability to explain from gender. Then we have Asian, Black, Native. And these, it did use the dummy variables because each of those is getting 1 degree of freedom. Right? And I had to do it that way to make it match the book. But what do you notice about race? It does not seem to be any difference among the races as to who gets hospitalized. Region of the country, not significant, although that's getting fairly low, but not significant. Education, not even close. Then personal health status, p-value less than 0.0001. So that seems to be one of the strongest predictors of getting hospitalized. What's your personal health status? Hey, that makes sense. I kind of expect that. And then the other one that's really, well, both of these, any limitations, physical limitations is highly predictive. Income is predictive. It's not as strong, but it's 0.035. So your income level is predictive of whether or not you get hospitalized. And then insurance. Remember that was insurance, yes or no. So if they have insurance, they are getting hospitalized much more often than if they don't have insurance. Okay, so now here's parameter estimates. Remember the discussion with collinearity? That also applies to logistic regression. So you should scan these parameter estimates and see if are there any of them that are negative, statistically significantly negative, right? Because if they're really 0 and you're not rejecting 0, then positive negative doesn't really matter. But are there any that are in the wrong direction? Well, positive would mean what? Well, we're predicting the probability of being hospitalized. So the probability goes up. If this goes up, then you should get a positive estimate. If the probability goes down when this goes up, then you should get a negative estimate. Right? So you might think, for instance, income. As your income went up, maybe you would be less likely to get hospitalized because you get better medical care through the year or something, right? So, but you have to remember these are set in there as dummy variables. So what are we comparing to? What's the estimate mean?
You're 34.
You're comparing to the reference group, which is the one left out, which is poor. Right, so high income has a parameter estimate of negative 0.92. What is that saying? The fact that it's negative.
Have high income, you have less chance of being hospitalized.
Yeah, if you have high income, you are less likely to get hospitalized than somebody with poor income. Poor or negative. In fact, they're all negative. And it actually, these two are, no, they're in the right order, aren't they? Because this is low. SAS alphabetizes things, which is kind of annoying sometimes. You can override it, but you have to look up how do you do it. But but it stepped down, -0.9, -0.6, -0.4, -0.2, and then the poor would be at 0. Okay? Then the next part of this output is odds ratio. I wanted to compare these parameter estimates with what we saw in that table 11.5. So I don't know if I can show both at the same time. Maybe if I do this. Look how smart I am. Okay, so look at what they have in the book for age, negative, or for intercept, negative 4.239, and then for intercept, negative 4.2388. So that's matching exactly to as many places as they kept. The negative 0.01 for age, 7.33, and so on. So this model matches what they had there. Now, do you agree that instead of T ratio, it'd be much more interesting to the public if they could see the p-value? You might have to explain what a p-value is, but that would be a lot easier to explain than what a T ratio is. What's even better output, I would not recommend this really in a paper or in a talk to non-statisticians. What I would recommend is a discussion of odds ratios. It tells you everything that that last thing told you, but it's easier to understand once you've been told how to understand it. So what is an odds ratio?
Is the number of times that you would expect that event of happening compared to your reference group.
Okay, compared to the reference group. And if it's a continuous variable like age, it's for a 1 year increase in age, or a 1 unit increase in a continuous variable. So the age odds ratio is 0.999.
It's the same it's nearly the same every year.
That's right. There's hardly any change across the ages. What's the null hypothesis? What value of odds ratio would you get if there's no change in odds? 1. So you're looking at whether this confidence interval contains the number 1. If it does contain the number 1, then you fail to reject the null. It does not seem to be an important predictor. But if it excludes 1, then you say, hey, that's an important predictor. Right? So age is clearly not important. The point estimate is almost 1, right? 0.999. So somebody who's 39 has 99.9% the same chance of getting hospitalized as somebody who's 38. Did I say 39? Whatever age I said. One less than that. Okay, now what about gender? Gender has an odds ratio of 2.08 with a confidence interval 1.4 to 3.0. Interpret that for me.
Gender and men are twice as likely to be hospitalized
Okay.
than men.
And how do you know it's women twice as likely as men and not the other way around?
It's men is 0, so men are the reference group.
Men are the reference group, and the smaller number always goes on the bottom, right? So it's a 1 for females and a 0 for males. So 1 will be bigger than 0, so 1's going to be on top. So the ratio of the odds is 2, so females are twice as likely to get hospitalized as males. And the fact that the confidence, you started to say this, Taylor, the confidence interval excludes the number 1, therefore
Oh, it's significant.
that it is statistically significant. We can rule out 1, which means no difference, as being plausible. Okay? All of the race ones are being compared to the reference group, which is white and other. And Asians are 0.8, black is 0.999, so almost identical to white and other. Native American 1.8, well that seems to be a lot bigger. You're 1.8 times more likely to get hospitalized if you're Native American. But what do you notice about the confidence interval? It's a giant interval. That's a good way to say it. It's really wide. And it includes 1. Right? Well, why would it be so wide, do you think?
Which one?
Native American.
Not very many people.
Not very many people in that subgroup. There weren't very many Native Americans in this 2,000 observation study. So we don't have a big enough sample. Standard error gets big.
Well, and is this one where you would identify as Native American? Because some living on a reservation do not have access to hospitalization. Would that ever be an issue?
It certainly could be an issue. Yes, definitely. But apparently what happened here is they just didn't get many people that identified as Native American in their sample. If I would, and they probably do in this survey, they would oversample some of these small subgroups to make sure that we get enough in that subgroup to make precise estimates.
So it's not always best to have just a random sample in that case?
Right. It's still called a random sample, but it's a stratified random sample, and you don't have to weight those strata equal to the population weights, and it's called oversampling. Right? But then when you compute your standard errors and all that, it gets more complicated because the standard error isn't the usual calculation. You have to account for the fact, well, this has been oversampled here, so you have to adjust it accordingly. But that's for grad school. Okay, and then the rest of these, what would be interesting here? Personal health status. Personal health, fair versus excellent. 1.1, but confidence interval includes 1. So there's not a statistically significant difference between fair and excellent, or good and excellent. Now, poor versus excellent, now you got a statistically significant difference. Odds ratio of 5.5. So you're 5.5 times more likely if you're in poor health versus excellent health. Right? So all of the intermediate health things didn't seem to matter that much or be that different from excellent, but then all of a sudden when it was poor, that made a big jump.
So is that in the book? Did they take out all of those and just put poor versus not?
I'm glad you asked that question. I don't know for sure what they did in the book, but here's my thought on that. When you have dummy variables, right? So when you're model building, if you have a categorical variable, and I'll say greater than or equal to 3 levels, because if it's 2 levels, then this issue doesn't come into play. But if it's a categorical variable with greater than or equal to 3 levels, so you have multiple dummy variables, then if one is selected, take them all. Because what happens if you pick one of them that was significant and you take the rest out of the model? What happens?
It's probably like a skew its influence.
Mathematically, what happens? Remember what the reference group is? The one you leave out. But you just left them all out except for one. So now what's your reference group? All the others pooled together. So then your test becomes, in this case, poor health versus any other health condition. Right? Which may or may not be what you're interested in. So people do these model selection criteria, stepwise or whatever, and it'll pick one of the dummy variables and put it in. The automatic selection procedures will do that. Right? It doesn't know they're related. So it picks one of them, puts it in, and doesn't put the others in. Then now your interpretation of that variable is different than what you might think it is. It's not that it's invalid. It's just you have to know what that thing is measuring. Right? So I recommend that if one of them is important, then you force the others in. So then it becomes a question about health status, not about poor health status. So you use all the categories or none of them.
Why is it greater than? Never mind.
Well, like I say, if the categorical variable has two levels, then this is a moot issue.
It's yes or no.
Right. It's yes or no, it's in or not. Right. Because you're only putting one in. Okay, then the last one is insurance. The last variable is insurance. 3.4 for an odds ratio, statistically significant. So you're about 3.4 times more likely to get hospitalized if you have insurance than if you don't have insurance. Do you remember the summary statistics we showed? Oh, not that. I clicked the wrong button. There. This is not it. There. Insurance, 3.1% versus 9.2%. And when we were looking at this, hey, look, you're 3 times as likely. What was the odds ratio we were just looking at? 3.4, right? So odds ratios, how many times more likely you are to have the event, whatever it is, in this case, get hospitalized. Okay, now, how do you pick the right model? They have a full model, they have a reduced model. How do you pick the correct model?
There is no correct model.
Well, there was,
Well,
you had the Aki last
Okay.
class.
Yep.
The way.
You can use all of the same procedures for model selection in SAS that you had available in multiple regression in proc logistic. So you have the stepwise selection, you have backward, forward, and you can do the AIC, right? And for nonlinear regression, AIC gets preference over things like CP and the others. I'm not sure why really, but it just seems to perform a little better. Let's take this full model, and I want to rerun it right here with the race 2 variable, and that's the one where I purposely forced the other and the white together. But that allows me to have an analysis of race, or a partial F-test of race, right? And then we can do our selection criteria, and it will either take race or not. So let's run that model. So now when I run that model, I get race 2, Asian versus white, black versus white. So these are all of the same ones that we had before. It didn't say versus white, but we knew, well, white was our reference group, so that's what they all were. So these are the same exact odds ratios that we had a minute ago. But if I scroll up, it'll give us, in addition, a test we didn't get before when we did it the other way. And that's this type 3 analysis, a 3-degree of freedom test for race. So the p-value for race, 0.7889. So race does not seem to be important. We looked, before we had to look at 3 different p-values, one for each of the non-white races. And then we looked and none of them were significant, so we said, oh, race is probably not important. But here it lets us take it collectively. Race collectively is not statistically significant. Okay, now, we got all those variables under consideration. I'm going to clear this output, and I'm going to go to my model statement, and I'm going to add selection equal, and let's do stepwise to start with.
Can you put the entry in that set then?
I'm going to just take the defaults.
Is that like 50?
Well, you know, I'm not sure what it is for logistic regression. That's what it turned out to be for regression. It's like 0.5. But yeah, maybe better. I don't want to have to do it twice. I don't want to run out of time. So SL entry. I better spell entry right. SL entry equal 0.1, and then we'll do SL stay at 0.1 also. And I'm also going to ask for the AIC to be printed. It didn't blue AIC, so maybe that's not valid here. It didn't like something. Yeah, AIC. It didn't turn it blue, so.
Is it because it was in your selection area?
Well, it was separated by space, so that's not it, but I'll just take it out. So the model that it selects, well, let me just go to the top. We'll work our way down this. Selection, stepwise selection procedure, it says at the top, and then gives you the information about the variables. And then step 0, the intercept is added. The intercept is always the first thing that goes into the model. Not sure why they say that. But then it says effect, down at the bottom, step 1, effect equal pH stat. Right, so that's personal health status. And so that was the most important variable based on, remember this is how the stepwise regression works? It had the smallest p-value of all of them, right? So then that one got added. Then they tell us the statistics from that model. And then at step 2, no effects from step 2 are removed. Well, we only got one in. But then step 3, effect of insurance is in it.
Did they add gender in step 2?
Did I go by one?
Yeah, right there.
Oh, okay, there it is. Yeah, step 2, add gender. And then it looks to see if the first one now is kicked out, and it's not. So gender's in, and personal health status, and then we add insurance, and then any limit goes in, any limitation to your activities, and then income goes in, no effects are removed, and then no additional effects, it finally says that here, no additional effects met the 0.1 significance level for entry into the study. So here's the summary of stepwise selection. So those are the variables that are in the model, and yeah, so if you look, these p-values aren't matching these p-values. So I always have to remind myself, now wait, are those p-values? These are the p-values that were used when deciding if that thing should go into the models, which is a different p-value because, you know, like at the step 3 when insurance got added, these variables weren't in the model. Well, now they are, so its p-value is going to change, right? So here's the type 3 analysis from our final model. All of them are highly significant. And we have parameter estimates, and then we'll have odds ratios after that. Let's go right down to odds ratios. Everything is statistically significant. It now breaks them up into each of the categories for the categorical ones. So now, not all of the income ones are significant. Notice that for low income versus poor, there's not a statistically significant difference. But all of them got taken into the model. Right?
So SAS automatically does that?
No, it's because I put it in as a categorical variable. So they didn't have a choice. But when it does its output, it breaks the categories up for you. But if I had put them in as dummy variable, I would have to force them in, and you can do that with an include statement. Include, and you just include equal and a number, and it'll be the first, like if you put include equal 3, it'll include the first 3 variables in your list of variables. So if you want to force the others in, you've got to put them in the first however many. It's easier to do the categorical. Okay? Percent concordant was about 75%. That's pretty high, so that's good. It looks like our model's fitting pretty well. So now I want to see this next model. Isn't this next model the one that I already forgot what the variables were? Did you guys write it down?
Gender,
Okay, there's 5 variables, right? Gender, personal health status, any limit, income, and insurance. 5. So now in my code, I did this for 1, 2, 3, 4, 5. Yeah. So this is the model. This is the final model, and I'm going to rerun it. Only I'm saving as an output data set the predicted logit. I'm naming it predicted logit, and I'm asking for PRED, which is the keyword for predicted value. But you have to remember, what are we predicting here? What is this logistic regression model predicting? Well, let's write out the model, then we're going to go look at this data set. All right, so let's write out the model. Let me go back to the output. These are our parameter estimates. So intercept is negative 3.97. Read it to me. 9.667. Okay, and then gender, and gender is a 0-1 variable, and it's 0.7458 times gender. And females are 1, and males are 0, right? And then the next one is personal. So it breaks them up for us and gives us a parameter estimate for each of them compared to poor, right? So that you can use these then as dummy variables. It's the only way to get a regression model with the categorical variables. You have to break them into the dummy variables. So this is, I'm just going to use the word fair, good, poor, and very good. And so this is plus 0.0947 times fair. And then the next one plus 0.3249 good.
Plus 1.6242 poor.
424. Okay.
And no, the word poor.
Oh, poor.
Not poor. Poor.
Gotcha. They put another decimal place in Spanish.
Then .1452, very good.
0.1452, very good. Okay. And then I'm tired of writing, so plus ... The rest of them. Okay. What's on this side?
Probability of being hospitalized.
Nope.
Natural log of y.
Nope. Close. Natural log of the odds of y being a 1 and y is hospitalized. Right? So this is the natural log of the odds of y equal 1. So when I print out that predicted data set, we can confirm how they're getting their predicted values by plugging in numbers into this. It's a lot more of them than would make this easy. I should have picked a different example to do that, but let's go ahead and print that out. Now remember, oh, yeah, there it is. This data set has 2,000 observations. So I just made a print with 2,000 lines about them. So clear down here to line 2,000. But let's just look at the first few of them. For the very first observation, it is a person who was 0 gender, male, excellent health, no limits to their functional whatever, medium income, but did not have insurance. That's kind of an odd combination. Usually if they're well, medium income, I guess. Insurance is usually tied to income, right? But they're in excellent health, so they may say, well, I don't need insurance. I'm in excellent health. Unfortunately, there's people like that. Right? So what happens when they have a car wreck? The rest of us pay their medical bill for them because they don't have insurance. How are we paying their medical bill? Well, taxes, some, but not so much. The premiums we pay for our insurance go up because overall,
The hospital has to make money.
the hospital charge, yep, exactly right. So anyway, it's some silly actuary that makes that decision. Predicted probability, 0.01046. Where does that number come from?
They use the odds.
Well, the predicted log odds, yeah, I don't know how to do this. You know what I'm going to do? Since I'm starting to run short on time, I got too many variables in here to make this easy. So I'm going to run a different model that only has a couple of variables. So then we can see how this all works. We got to get from the output from this equation to the predicted probability. Okay? So let's go back and run. What were my most important variables?
Personal health status and gender.
Yeah, let's run those 3 variables. So we'll take out their income and any limit.
Except for the self-office.
What's that?
Except that your pronouns will have the, we can print them.
And I'm going to say obs equal 10. It's only going to print 10 observations instead of 2,000. Oh, I see what you're saying. So I need to delete these variables. Okay, so now let's go edit our model here accordingly. Our parameter estimates. That's my eraser. I'm just going to scroll that down here. I don't see why I have to write them all out when they're written out there. I'm going to put them there, but I got to go back and get our first person, and let's write that out. So hospital is 0, and then gender is 0, and they were excellent health. And insurance was 0. So I have those 4 variables, right? Now we're going to scroll back up here, and then we're going to use their parameter estimates, and I want you to use your calculator and compute the model predicted value for log odds. So we'll have the intercept, then we'll have gender times 0. Hey, that's easy. And then we'll have the excellent. What do we do with excellent?
It's
All
added.
those are 0.
All of these are 0. Excellent is part of this intercept, right? It's the reference group. Hey, that was handy. Right? So maybe should use the next guy down, but so all of those are 0.
And insurance is So it's negative 3.967?
And insurance is 0. Okay, so
That's great.
negative 4.3577. That's pretty easy to do. So that's the log odds. So for that person, the log odds, oops, I forgot to pull this along. Is negative 4.3577. Get from log odds to odds by doing what?
Raise it to E.
Exponential of negative 4.3577. What's that number?
0.012807.
12807. And how do we get from odds to probability?
Odds over
It's
one
e
plus
to
one.
that plus 1 over 1 plus e to that. It's,
Oh, we already did the e to that.
oh, okay, so it's 0.0128107 over 1
Plus that.
0.02.
Over 1 plus that.
Yeah.
1 plus. And I went ahead and wrote it out 1 plus, but obviously 1 plus that would be 1.00. Whatever. All right.
0.012646.
0.26466. Okay? So there's our predicted probability. Now let's go back down and see what their output was. Predicted probability, 0.01265. 0.01265.
So how do you test how well these models work?
It's a little tougher with logistic regression. We don't have an R-square, but we have something called a pseudo R-square. I talked about that a little bit before. I put an option after my slash on the model statement that said R-square. So somewhere in here, that should be in the output. Let's see if we can find it.
That's what I was just wondering, like, what are your examples?
So it says R square 0.0472. And then the max rescaled R square, and our book does talk about, no, our book doesn't, but the chapter in the old book talks about this max rescaled R square, which is, most people say that's preferred, but it's kind of a pseudo R squared, but it's 0.11. So the interpretation is supposed to be the same as the R square used to. You want it to be close to 1, and that's not very close to 1, right? So really it's saying, these are the best variables you got, but it's hard to predict somebody's getting hospitalized. There's a lot of random noise in that data also, like getting hit by a car, right? That you can't predict based on all these variables. So, but it's the best you can do. So you go with it. Okay. Well, I will let you go, and the homework over logistic regression will be out of this book, and I have it pretty much ready to go already, so I'll get it posted out there for you. It's only one problem out of this book, but it's one problem with like M parts or something, right? So,
Oh, gosh.
and you're going to run it in SAS. So I will help you with SAS code. If you get confused, just email me and say, here, this is where I'm at. I don't know what to do next. Good luck.